Good morning and good afternoon, everybody. Thank you for joining tinyML Talks. This is the first tinyML Tokyo meetup session, and it's a great pleasure for us to have Andrew Reusch from OctoML. He'll be talking about microTVM, a Tensor Compiler for bare metal today with us. And I see that already a number of participants are joining in. So as more participants continue to join in, we'll move forward. Before I can introduce Andrew, let me go over and thank our sponsors, without whom it would be very difficult for us to share these excellent talks and presentations with you. So we would like to thank ARM, the tinyML strategic partner, as well as our other sponsors of the tinyML talks, Edge Impulse, Kixo, DeepLight, Maxim Integrated, Reality, AI, and SynSense. I would also like to remind all of you that later in February, we have the next tinyML talks, which would be on February the 2nd, Tuesday, the usual time at 8 a.m. Pacific time. And this time, the presenter is Martino Sorbaro, who is an R&D scientist at SynSense. If you would be interested in presenting as well in any of these sessions that we organize, feel free to contact talks@tinyml.org. And today's talk, of course, I forgot to introduce myself. I'm Sakya Dasgupta, founder of EdgeCortex Inc., the local committee here in Japan. And we are really also looking for other leaders who would help us grow the community of tinyML here in Tokyo, in Japan. So if you're interested in joining the local committee and leading our efforts here for tinyML organization, feel free to contact talks@tinyml.org, or you can also reach out to me directly, and I'll get you in touch with the other organizers. So with that, it's great pleasure for me to introduce Andrew Reusch, today's speaker. Andrew is a senior software engineer at OctoML, and he's the main lead and core contributor for the microTVM project, which is also today's topic of the presentation. Prior to OctoML, he worked as a digital IC design and embedded firmware for medical devices at Verily, an Alphabet company. And he also holds a Bachelor of Engineering in Computer Engineering from the University of Washington. So without further ado, over to you, Andrew. Why don't you go ahead and share your screen? And we are looking forward to your talk.
Great, thanks for the introduction, Sakya, and it's great to be here. I'm excited to explain more about microTVM and to everyone today. Let me just share my screen. And is everyone able to see that all right? Okay, great. So without further ado, let's see, we'll get started. So let's see, I just wanted to start with just a brief overview of kind of how the talk's going to work. So at first, I just want to start explaining what is microTVM, just to introduce those of you not familiar with it. We'll talk a little about how it works. We'll do some demos for you guys. We'll talk about future directions for the project, and then we'll have more Q&A. So let's get started. So what is microTVM? microTVM is using an open source project called TVM to translate models from a model description language like TensorFlow, PyTorch, ONNX, Keras, any of these kind of very popular frameworks, into something you can run on a bare metal device. And the next question you might have then is, what is a bare metal device? And you might not necessarily have this as much if you're in the tinyML forum, but just to be specific, to microTVM, bare metal doesn't just mean running on Raspberry Pi. These usually have some kind of a traditional operating system like Linux on it. It doesn't mean like a reserved cloud instance in the cloud. This usually has virtual memory, and it doesn't mean running outside of a virtual machine hypervisor. Again, this is just a traditional operating system like Linux. Bare metal is often thought of more for microTVM's purposes as IoT class devices. So some things like Microsoft Azure Sphere, which is something we've done work with. Arduino is a great example. In general, you can kind of think of these as Cortex-M class microcontrollers. And let's be even more specific here. MicroTVM works, it doesn't rely on any sort of operating system. It doesn't need any concept of files, DLLs, shared objects, memory mapping, and it doesn't assume the presence of any kernel. It doesn't assume any sort of virtual memory, and by that token, it doesn't use malloc. It doesn't use any sort of like resource allocation as initialization from C++. It can't use exceptions for that reason. And it doesn't use advanced programming languages. You don't need anything like Rust or MicroPython, although we do like those things and you could integrate with them if you wanted to. And so you might ask yourself, why do we need a separate thing here like microTVM? Why can't we just use a traditional framework like TensorFlow or PyTorch or Caffe or any of these existing solutions? And to answer that, I thought we could consider like a toy problem here, which is we call the deployment challenge. So if you put the different frameworks that you might have models in down the left, and then you across the top here, we put the places you might want to run those models. We can just ask ourselves, can we just run a model out of the box from one on the other? And so many questions. And in some prolific targets, you can see that we have broad support. So on x86 machines with traditional operating systems, on GPUs, many of the frameworks support these natively out of the box. And we see that broadly. But once you start removing these abstractions we talked about and moving towards bare metal, things look a little bit different. In some cases, we get lucky. Models, for example, that you can translate into TensorFlow Lite. It has a great runtime for ARM CPUs called TF Lite Micro. And so wherever TF Lite Micro is supported, you can run your model. But in other cases, if your model is in Caffe, or I guess not to call it any frameworks, but if your framework can't particularly translate, if the model can't be translated from your framework onto something compatible with bare metal, you might be more out of luck. You might have to find an experimental project that supports microcontroller execution from that framework. You might translate the model into a different framework, or you might just have to retrain your model in a different framework. And this gets really tricky, especially for embedded projects where they may not know exactly what target they're running on when they start out. So I want to talk about so why is bare metal so hard to actually use? And basically, I can think of a couple of different reasons. The first is that there's just less abstraction, which means there's less tools as well. So there's no files. Things like CPU time is harder to schedule, which you don't have primitive multitasking. Resources are tighter. So memory is typically measured in kilobytes rather than gigabytes on these systems, and so doing things like parsing JSON can be quite burdensome. And then finally, there's kind of like what I think of as sort of the special snowflake property of these projects. It's just that per chip or even per project, things can change quite a bit. There can just be a particularly unique demand placed on the firmware. In some cases, maybe you can't run the CPU for longer than 15 milliseconds because the attached power supply, needs some time to recharge its capacitor. In others, maybe you can't define too many global variables because the flash to RAM loop might take too long to initialize, and that might add jitter to the system that would be unacceptable. And then there's always, just very specialized linker scripts. And all of these demands, by the way, are not, they're not hypothetical. They're things that I've encountered in my somewhat short career in embedded systems. All of these factors compile to make it really hard to build common libraries for these scenarios. So instead of building a library, we've decided to build an entire ML compiler. I want to talk to you guys a little bit about what TVM is first before we dive into microTVM. TVM is the parent project of microTVM. It's a deep learning compiler. TVM takes models from all these popular frameworks we mentioned, and it knows how to produce code to run on each of these different backends. So kind of already we're starting with this assumption that each runtime environment is a little different from the others. TVM has quite a bit of traction. It's been used around the industry at a number of major companies. And it's got a growing but already quite large open source community. I think it's up to at least 460 contributors last I checked. So growing every day. We also have a conference this past, I think this is the second iteration. We had this last year. I think we're up to about 950 people at least. So there's a lot of interest in general in the framework. So having said that, I want to talk a little bit more about the microTVM approach to this problem. How do we use microTVM in a bare metal environment? MicroTVM takes like a batteries included approach. So it depends only on the standard C library. It's compute centric. MicroTVM doesn't really care how you configure your SoC. It assumes you can kind of handle that. It just takes care of the process of running computations. To address the SoC configuration problem, it actually integrates with RTOS like Zephyr or Embed to handle that. That said, you can actually bring whatever configuration or project scaffolding you want to, and we'll talk a little bit more about that later on. Finally, microTVM aims to be transparent. MicroTVM can generate C source code, and you can tweak, inspect, modify whatever you want to do with that source code. So you can see exactly what it is that you're running on your device from the beginning. So, okay, so having given you a little overview of what microTVM is, now I want to talk a little bit about what how microTVM works. And I want to start with this fairly simplistic view because we're going to go quite deep in just a minute here. So, so the typical scenario is we start with a model that we've trained up, and we want to then import it into TVM and compile it into C so we can deploy it on a microcontroller. To do that, we're going to link it against the generated code from TVM against a main that configures the SoC and executes the model inference task. We'll place that on an embedded device. So I'm going to talk a little bit about every different part of this process, but to begin with, I want to talk about the left-hand side here, which is the model compilation part. And I want to start with this here because I want to show you just how accessible your model is as the TVM compiler morphs it from TensorFlow or Keras or PyTorch into C. So the first thing you want to do when you begin working with TVM is run a model import. And that ingests your model into TVM, and it produces a relay module. A relay module is sort of TVM's internal high-level model representation. It's hardware agnostic, and it contains a bunch of smaller canonical operators that are often composed to represent operators from other model formats. So for example, here, I think here I've imported a Keras model that just contains a con2D, but in Keras, I think that also implies maybe a right shift and a cast, depending on how that all works. So, so those operators have been inserted here, and that's sort of a way that allows TVM to import from so many different frameworks and yet still achieve reproducible results. Each operator in your model is represented here in this graph. You can save this to file, you can tweak it. As you can see, this is fairly human readable. It's just like another programming language. And you can, if something doesn't import right, you can modify it here. Once you've imported your module, then the next step is to actually optimize it. And this is kind of where TVM, you might ask, well, now that TVM knows that we have to do a comp2D operator, how does it know how to implement it? And one of TVM's techniques is called AutoTbm, which is sort of a data-driven template-based approach. It allows TVM to sort of start with a template implementation of each operator and then tweak the template to achieve optimal cache memory use on your particular target with your particular software stack. Once this process is finished, you're left with a code in a language called TensorIR. And this is kind of a low-level compiler representation. It's specific to your hardware. For example, it's the template that's going to be used to implement each operator has been chosen, but it's not specific to the type of code that you're going to generate. And I'll talk about that in a minute here. Roughly what happens is each operator from your model is translated into one TensorIR function. And this is kind of useful when you want to, if you want to do things like here you can see that it's allocated some scratch space here. And so you can actually go through either kind of yourself or you can write compiler passes that traverse these generated functions to inspect them. So finally, then you can take your TensorIR and you can generate C source code, or actually you can generate LLVM IR from this as well and generate a binary code, which is sort of like your implemented operator functions. Here for each TIR function, a C function is produced. And again, this corresponds to essentially one function from Relay. Going to C here is the most compatible and flexible here, but you can, I should say, it should also be mentioned that you can generate binary code, which may kind of, especially in the future, allow you to leverage better intrinsics for each target. Okay, so are we done? There's a few other things. Along with models, you typically wind up importing parameters, and these are, or weights. These are kind of like the parts of the model that you train in your training step. And so TVM also knows how to accept those and include those in its optimizer. As a direct result of the compilation process, you then get simplified parameters, the compiled operators, which we just mentioned before. And then finally, you get a thing called the operator call graph. Now, I mentioned before that each operator function in Relay is translated roughly into one C function. The operator call graph then kind of explains, now that we have all these functions, how do we call them, in what order, to complete our original model inference task. So before we leave this topic, I just want to talk a little bit about the process of running a model end to end. So to do that, we're going to take our 3 compiler outputs from before. That's the graph JSON, the compiled operators, and the simplified parameters. And we feed these into a graph runtime. The graph runtime reconstructs the graph JSON in memory. And you can see here that's created this call graph for a comp2D plus a bias add here. We feed in the simplified parameters to the graph runtime, and those together with the inputs are attached to the graph. And then to actually drive the inference operation, the graph runtime just traverses the graph, and wherever it encounters a generated function, it looks up that function in a registry and invokes it. Okay, so we've talked a little bit about the process of compiling and generating operator code. Now let's talk about the process of actually putting that onto a microcontroller. So that's where we build a binary firmware image that we can load. Okay, so before we talk about that, let's look at all the different pieces we might have here. Okay, got an extra transition here. So we have the compiler outputs on the left here. And then, so we've already talked about those. On the right, we have a couple different things. We've got the model inputs, and that's kind of the data from the user. We've got a main function, and that handles the process of configuring the SoC, setting up any clocking and cache configuration, and doing any sort of system startup. And then on top of that, we've got 2 additional libraries we can use. One is the graph runtime, and I just went over kind of how that worked on the previous slide. The other thing we have is an RPC client and server, and we'll talk a little bit about that in a minute. There are a couple different ways to deploy things with TVM. Here we're looking at what we call the host-driven approach. And we're calling it that because we actually instantiate the graph runtime on a host x86 or otherwise traditional computer. And then we use this RPC client and server to actually drive inference on the device over a channel like UART or semi-hosting or USB. So in this case, we actually have the board attached to a computer, and we're driving inference from the computer. But what's great about this is the firmware that's running on the device is almost always reusable, and it doesn't change very much. And it's particularly useful for experimenting with new models. Let's just try out this model and see how it runs. And it's also useful for kind of our optimization passes. This is the AutoTbm thing I mentioned before. The second way to run things is kind of the standalone way. And that's where we just move the graph JSON onto the device. the advantage of this, of course, is that you don't need an attached computer to run. However, you do need to write, of course, task-specific code to load the graph JSON into the graph runtime, and then actually instantiate the graph runtime and drive model inference. So finally, everything I talked about here was quite a bit of, there are a lot of different pieces here. So there's physical hardware, there's the TVM compiler, there's the compilation toolchain for your particular target, the RTOS, and any sort of SFC configuration code. And there are a lot of moving pieces. So in order to build sort of an effective way to collaborate, we've produced a reference virtual machine. And this is kind of a way of freezing all the software dependencies so that if we're trying to reproduce bugs or collaborate on things, we try to get to the same configuration as much as possible. When we're working with reference VM, and I'll show you that in just a minute here, you can start this in sort of your favorite hypervisor. You can use VMware, you can use VirtualBox or Parallels. And then we attach the hardware to the virtual machine with USB pass-through. There's a tutorial you can look at online if you want to see more about this. Okay, so I think I've talked enough a little bit about how microTVM works. Now we want to show you a little bit of a demo. Let's see, before I go to that, I don't see any questions yet, so I'm going to go through the demo and we'll come back to those. Oh, go ahead.
Let me just ask one question, and while we're waiting for others to come in, if you can tell a little bit about how is quantization, if at all, taken care of with microTVM? So one of the features, of course, when we're working with tinyML, is that in majority of the cases we would have to do some kind of quantization of the models. Also in TVM, there is this QNN dialect. So if you can tell a little bit about if that is already integrated with microTVM or there is some other way in which quantization is handled.
Yeah, absolutely. So quantization is a complex topic, and actually I should have some slides for that here, but I don't have too many things to point at. But what I will say is that microTVM works especially great with already quantized models. We can import models that are quantized in other frameworks using this QNN dialect. And that still follows the same import process that I just went over. So the process for using those is exactly the same. In fact, the demo we're about to show you uses a quantized model. TVM can also quantize models to a limited degree that were previously in floating point at the time of import. Currently, TVM's approach to this is effectively a global scale quantization where the transform applied to each operator is kept constant throughout the entire model. With that said, keep your eye out, and I'll talk a little bit about this more in future directions, because there's quite a bit of work being done on that to enable data-driven quantization in the coming months. So
excellent. I see that there is one more question, so if you don't mind, we can take that as well.
Yeah, sure.
Maurizio Gentelli asks, is there any limitation on the operators supported for the different frameworks? I guess different frameworks like PyTorch, TensorFlow, Lite, etc.
Yeah, definitely. So with everything, so sort of with any of these model frameworks, there's always going to be a set of supported operators. But with that said, TVM has fairly broad support for operators from other frameworks. And as well as a defined pathway to add new ones. And I think another thing worth, let's see, I guess I would say it. I think there's a lot of literature out there on kind of the models that TVM can run, and so I'd encourage you to take a look at that. And I just say over the top, in addition to that. Short of dynamic models and models with control flow, kind of, I guess, in terms of the operators, microTVM aims to support the same set of operators that TVM, regular TVM supports. So, okay, so So with that said, let's go to our demo. So I'm just going to move my presentation aside here. So I'm going to give you guys a quick overview of what I've got connected to my machine here. Here we've got an STM Nucleo 746EG board, and that's the same board we've been using kind of with our earlier blog post, and that's attached to my laptop here with a USB cable. This is just the plain development board you can buy online. And for this demo, we're going to be using a Jupyter notebook to kind of inspect and play around with things. And with that said, all of this code is available on this on our microTVM blog post repository, and there's a link to that at the end of the slide deck here. So you guys can all play around with this at home if you got this hardware. So I'm going to go through a quick walkthrough to talk about to show you how we run models on device in the host-driven way. And then after this, we're going to show you a slightly different demo where we run a model in the standalone deployment way. So running model on device always starts with importing a model. And here, I'm actually going to reuse the blog post utilities to do that. However, I think it's important to point out that at the end of this process, we're going to get a relay model and a set of parameters. And that's the same thing that you're going to get when you use any kind of imported, any kind of TVM import front end. So if you're importing a TF-Lite model, you're going to get exactly this. I'll just start by running that, and let's make sure I've got this thing working. Great. OK, it looks like it's worked. So now that we've got our model into TVM, let's print it out. And what model is it we're working with today? We're working with this IFAR10 CNN model. That's just kind of a classic convolutional neural network model. We've talked a little bit about that on our microTVM blog post earlier this year. So if you want to read a little bit more about that, I'd encourage you to take a look at our blog post. The first thing you should do after you import a model is you should look through the model to make sure that you got what you wanted. And here we can see this is incredibly small font. I'll make it bigger just for a second. I don't expect anyone to read this giant wall of text, but you can see like, yeah, there's a com2d, there's another com2d, and there's a third com2d in here. So, you know, this is kind of looking like the model we wanted. Let's go back to normal size because I really don't expect everyone to read a wall of text. We also get some parameters, and let me just make sure we've got this working here. Okay, and here I'll just print the parameters by name and weight, and that's kind of just a good way to kind of sanity check things. Now, in the real world, you should do much more than just print out the model and parameters. You should sort of exhaustively run it and make sure that you're confident in the validity of the model that you've imported here. But just for the purpose of the demo, we're gonna go with this for now because we've looked at this before and we know it works. Okay. So now we've got the model imported, we're going to try to run the TVM compiler. And before we can do that, we need to describe the execution environment to the compiler. And we do that through a TVM target. So here we describe a target with a pretty long string. And I'm going to go walk through this real quick with you guys to explain all the different things we can configure with the TVM compiler. The first part is we're telling the TVM compiler we want it to generate C. So that means we want to generate source code. If we wanted to generate binary, we could actually just change this to LLVM and it would generate a .o file for us. But for now, since we want to kind of inspect the generated code, we're going to stick with C. This keys equals RMCU is a flag to our optimizer, and that basically enables the schedule templates that we would typically use on an ARM CPU. MCPU Cortex M7 explains which kind of intrinsics we can use with a particular model. And it's also passed to the downstream C compiler. Link params here is a particularly useful one. It tells the TVM compiler that you would like to embed the parameters you're providing to the compiler into the generated code as a constant. And that winds up placing the parameters in Flash. So for embedded targets where RAM is really precious, this option here makes it oftentimes will make a pretty big difference whether a model can fit on a target or not. The dashed model equals STM. That's actually mostly unused, but it's a hint to the compiler of the particular CPU model that we're using. Finally, these last two flags are actually particularly important. The runtime equals C. tells the TVM compiler that we're going to generate code to run on the C runtime, and that's the runtime we use with bare metal. This dash systemlib equals 1. It tells the TVM compiler that it's an option we use with the bare metal deployment. If we weren't using the C runtime, we were just using this on a Linux system, it's possible we could generate the model, compile it into, we could generate a shared library from the model, like a .so, and then we could just DL open that model and load it into the TVM runtime. Since we don't have DL open and we don't have files, we need to do something else, obviously, here. Systemlib is kind of TVM's simplest way to load a model into its runtime. And it works using sort of a global function that we'll show later. So we use it here with microcontrollers. Okay, so having gone through that, we can now run the compiler. And to do that, we just set some compiler options here and pass our relay model target and parameters to relay build. This is the central compiler function, and you can see here we get out the 3 outputs that I was talking about earlier, the graph.json, the compiled model, and the simplified parameters. So let's create our target and run the compiler here. Great, okay, so let's see if we can take a look at the generated output here. Here's the generated C code from our CNN model. The first line here, we see like a TVM target description, and that's kind of useful if you're going to generate a few of these different files. You can kind of verify that you're using on the right target. There's some includes from TVM. These are just header only things that there's no like the library dependencies. I'm sorry, I shouldn't say that. These are just sort of like core runtime includes here. Then there's some includes for math functions. And then finally down here, you see we have our optimized gem implementation. That's what sort of allows us to achieve good performance for convolutions on ARM processors. So this is quite long and we could keep going through it, but I'll skip the rest of that for everyone's sanity. We can also look at the generated function registry. And you can see that that's just an array of function pointers as well as a sort of a long string that's used to look up the functions. And this function registry is registered into this system library that we're mentioning earlier. This is kind of how the TVM graph runtime looks up the various different operators to execute. Finally, we can look at the simplified parameters that were generated. And you can see that these parameters, actually, the shapes are very similar to the ones that we input, but the names have all been changed. And that's just an artifact of the parameter simplification process. We can also print out the graph.json just so we can look at all the different compiler outputs. And so just below that, we have that here. Here you can see this nodes list gives a list of all the different it gives a list of all the different parameters, inputs, and operator functions here. So this is what the graph runtime uses to reconstruct the execution graph. Okay, so we've run our compiler, and now we're going to do the second phase of things, which is to build a host-driven binary. At this point, you could basically serialize these things into, you could save these things to a C file and then inject it into your own build system, however you'd want to. Here, we're going to use the same build system we use with AutoTBM. And so that sort of allows TVM to drive the compilation process here. I've run this here, and you can see Zephyr is being invoked in the right-hand terminal window here several different times. What we're doing here is building several different libraries. We're building the RPC server library we mentioned earlier. We're building a common runtime library. We're building the generated operators. You can see there's some warnings here that it's complaining about some type hunting. We're building basically the sort of RPC glue logic into different libraries. And the idea with that is that we build kind of the common libraries just once, and then when we're performing AutoTBM, we just need to iteratively build incrementally build the generated operator libraries. this takes just a second here, and it's all finished. And so now I can generate, now just to kind of prove that we did generate a binary here, we'll run this ARM EAV size tool, which basically just prints out some characteristics of the binary. We can see we printed about, or we can see we used about 130K of flash, and this BSS segment here is all of the pre-allocated RAM that we've dedicated to our model here. So the last thing we need to do before we can run our model is to generate some test data. And we'll do that using the utilities from the microTVM blog post here, but you could essentially generate NumPy arrays that contain the test data, and that would be sufficient. Here, I'll just print out the test data so you can see that we're actually driving this model with an image. And this might look a little bit strange because there's 4 channels here, but and one of them is always 0, but we actually are using an ARM intrinsic here that makes it more convenient to use this 4th channel to have a 0 4th channel when we're driving inference on the chip. So we do expect that, and we see that the other 3 channels look kind of like image data. Finally, we'll flash this. So we're ready to flash this and run this onto the attached microprocessor. So to do that, we'll construct this session object. And that's kind of a glue object that's used. You can use both for kind of experimental host-driven models, and you can also use it for AutoTbm. This flashes the attached microcontroller and then opens a channel to the RPC server on the device, in this case over UART. Once we've done that, we'll instantiate the graph runtime on the host computer and then set our model input. You'll note that we don't need to set parameters here because those are have been set in Flash. And then we run the model. Finally, we get a reference to the output data and convert that into a NumPy array. That's kind of important to do because converting it to a NumPy array forces TVM to download the data off the device, and that makes it safe to exit this with block and therefore disconnect from the RPC server. So we'll run that, and when I click this run button, you'll see the LED flashing here. That's kind of indicating that the model is being downloaded, or the compiled model is being downloaded. And just wait a few minutes for it to flash all the data. You can see that the RPC server has booted up, and let's see here. We might be having our classic demo problem here, so, and I think I know what's going on here, but let's wait a second for this to time out. Yes, that's right. One limitation we have sometimes with our VM-based approach, at least on my Mac, is if you may run into serial corruption here. So I'm going to rerun this and see if we can see any output here. While this is rerunning, I see a question here. Doesn't GraphJSON create memory overhead? And you're absolutely right, it does. And we know that. We're currently working on an ahead of time compiler, and we'll talk a little bit about that in a second here. Okay, great. That was the problem, and I was right. So I'll get back to this question in just a minute here. Let me finish this tutorial here, and then we'll talk about kind of the future of microTVM. So here you can see we've got an output from the CNN. The last thing would be to check our work on the host. And so to do that, we're going to reinstantiate the model, targeting it at LLVM, but without any of these extra parameters we used before. And that allows TVM to run this model on the local CPU rather than on the microcontroller. Here you can see we got the same answer here as we did on the microcontroller. Now, of course, when validating a model, of course, you should do a lot more work than just this, but this is kind of what we're doing for our demo today. Okay, so now I'm going to switch gears. I'm going to show you quickly the standalone. I'm going to show you running the model in the standalone excuse me, I'm going to show you running the model standalone. And that's inside this microTVM block repo under standalone. What I've done here is I've created a Zephyr project here. And there's a couple things I'm just going to point out real quick, and then I'm going to run this, and then we can move on to kind of future directions. You can see that I've encoded the different compiler outputs here in C. So the graph JSON here is a static global constant here. The model inputs have been similarly encoded. And then you can also see this. I'm sorry, I showed that very quickly. So this is just an array, and you can see that every fourth entry here is 0, just as we were looking before. And then finally, you can see this model.c, and that's that same function that we were talking about before. There's a small main that that effectively initializes the runtime, loads the system library, creates the graph runtime, sets the input, and run. This kind of looks very similar to the code that we use in Python. It's just written in C. So once the model inference is done here, it prints it on the serial console, and we'll be able to see that in Miniterm here in just a second. So just to make sure I'm not cheating, I'm going to remove my build output here. Now, I'm going to build this. And one thing I'm going to say real quick here is that kind of to this question about graph JSON, doesn't it create memory overhead? You're absolutely right, it does. And one of the things that we're going to do here is we're actually going to show that we can switch boards very quickly to a board with even more RAM. It's worth saying that we're able to use the same model, generated model that TVM produced with a Cortex M33 board. That's this NRF 5340 board here. And we're able to do that because TVM is able to sort of like leverage the same intrinsic on multiple boards, and then by our strategy of depending on an external library or RTOS for RSSC configuration means that kind of the delta change we needed to make here was to change the build command to tell Zephyr to use a different board. So now that I've built this, I'm just going to switch boards quickly here. You can see this guy is powered up. I'll just make sure it connected to the machine here. Okay, let's see if we can flash it. You should see this LED blinking showing that it's erasing. This will take just a minute because it's going to flash both the model, but also all of the parameters from the model into Flash. And okay, and then we should be able to see the model output here on the serial device. And you can see that indeed we do get a match here between the output we computed on the CPU and our standalone output here. Okay, so that's kind of our demo. I'd like to quickly talk about some future directions for microTVM, and then I'm going to turn it back over to Sakya to talk about, to give you a few last words before we take questions. So, you know, in 2020, we started, and I have to say thank you to my colleagues for kind of kickstarting microTVM with kind of an experimental approach to use JTAG only to run on an attached CPU attached microcontroller. In June, we posted a blog post kind of detailing the road to a standalone runtime. And then in December, we demonstrated a standalone runtime. So that was kind of our 2020 year. Next up for microTVM, and speaking to this question about overhead, we're working now on an ahead of time compiler. And the way that works, you can see it's fairly straightforward. It's like you take what the graph runtime would have done, and then you just translate that into C code. We actually have sort of a V0 of this working right now, but we're actually going to rewrite it to take even more advantage of graph level optimization in the first quarter of this year. So be on the lookout for that. We'll be working on hardware world acceleration. And to the question about quantization here, we've done some work to work towards data-aware quantization. And so we expect that work to be landing in the coming months here. We also did some work last year with ultra low bit width quantization. So, sub-byte data types. And we think that would be really cool to integrate with microTVM. Heterogeneous execution is going to be a really interesting thing that we're starting to work on this year. ARM has actually done some work on this with their their U55 accelerator. And so we expect some more work along that. Related to this is memory planning. Our current memory planner has some limitations. It's not aware of sort of memory, accelerator memory, or any kind of, can't make distinctions currently between different types of on-device memory, but we are working on basically improving that with tensor pinning and an accelerator-aware memory planning, and we expect that to land in the coming months as well. We also expect to increase our operator coverage, and we're really excited about a project called auto scheduling, which allows you to describe hardware to TVM in simpler terms, and then allows TVM to derive schedule templates for operators around your hardware, rather than requiring you to write fully templatized operators for each different model of CPU that you're using. Finally, the last thing we want to work on is, well, I guess the next thing we want to work on is the developer experience. We know in particular it can be really hard to get started with TVM, and we expect to improve, to make significant improvement to the getting started experience and the TVM runtime to make it more production ready. Finally, we'll be adding some more documentation, especially documentation targeted at developers from multiple backgrounds. So please keep an eye out for that. We love contributors to get involved with TVM. TVM has a vibrant open source community. Again, I mentioned over 460 contributors. We've kind of detailed the projects we're going to be working on in the next couple of quarters in the M2 roadmap here. And I'd really encourage you to take a look at that if you're interested in kind of where the project's headed in the medium term, and especially if you're interested in contributing. We're always open to PRs for bug fixes, enhancements, doc changes, et cetera. We'd really encourage you to check out the forum, which is linked at the end of the slide here. And get involved there. Finally, just have a couple of pointers here at code and the tutorials that we showed today. And I guess I'll turn it back over to Sakya for some more from tinyML.
Excellent. Thanks a lot, Andrew. So I see that there is already there is a pending question here. So maybe if you don't mind, you can just keep your last slide open while we take this question, and if there are any others. So in this question, Islam Mohammed, he asks, since microcontrollers' memory are limited, and for the bare metal, we provide linker according to the SoC configuration, does microTVM generate code for any kind of memory configurations of such SoCs?
So microTVM doesn't generate any linker scripts. It generates just sort of the C code that is needed to implement your model. But with that said, we've defined a fairly simple integration between that and kind of the host. I guess we've currently demonstrated this with a RTOS like Zephyr, and we defined a fairly simple API that you can use from your Zephyr main to invoke the generated code. Now, when you're asking questions more towards linker scripts and memory pinning, that's something that we're intending to work on in the coming months here, and we expect to make significant changes to the way that we do memory allocation right now. Currently, what we do is we allocate things globally in RAM, and you supply the a buffer that contains all of the tensors. And in the future, we'd like to make it possible to split this buffer, to have some tensors live in sort of shared memory between accelerator and CPU, or whatever particular memory region you might like to use, particularly if there's power domain considerations.
Great, thanks a lot. Maybe another question from my side. Could you talk a little bit about if right now you already have support for, and we know that TVM already supports in non-convolutional operators in some cases. Can you talk a little bit about the microTVM also supporting, for example, speech or audio processing type applications, because that's another very popular applications in the TVM, tinyML community.
Yeah, definitely. So we have done some work with that. I'd encourage you to take a look at our Azure Sphere blog post, where we show some work with audio as well. We do support we do support different operators like that as well. I think I think that we should be able to. I guess I'd point you to our TVM tutorials to see a better picture of the supported operators. In general, microTVM should be able to run most all operators that are supported by TVM in general. And I guess I would say an open area of research with TVM is kind of the more dynamic model support and control flow and all that. So that's kind of a work we'll probably be expecting to get to a little bit later on. So
excellent. So I think I see there is one more question at the Q&A. If you can take that,
sure.
Andrew.
Yeah, let's see. So I see, does microTVM have built-in tools for inference benchmarking? So actually, I guess one of the we talked briefly about AutoTBM, but we didn't go into detail about that. And one, I guess the quick way to talk about AutoTBM is that what it does is it takes this schedule template, it compiles a sort of prototype program, and then it times that compiled operator on the device itself. And so as part of that, there is a tool that you can use to time execution, and microTVM does support basically runtime benchmarking. However, I think at kind of in the future, we're very interested in adding support for other types of benchmarks, such as power, memory, etc. So yeah, definitely keep your eye out for that.
That's great to know. Maybe a final question from my side. You did mention in your future directions that there is already some plans for heterogeneous kind of support with ARM contributing towards that. Related to that, if you can talk a little bit more about it. So for example, I noticed that your targets right now are the Cortex-M processors. And in this case, how does it change if you have, let's say, a built-in NPU available on your, alongside your CPU?
Yeah, definitely. I mean, I think that, so I'd preface this by saying that this is pretty early days for heterogeneous execution on microTVM, and we expect a lot of this to change. But, a lot of this work with the NPU and memory planning are deeply intertwined. A lot of the graph level planning revolves around placing inputs and outputs to these specialized accelerators in particular memory regions, as well as kind of handling, doing handoff. And so kind of for the graph level memory planning, we have that ongoing memory planning work. For the handoff, we actually have something already in the TVM code base, the bring your own compiler flow. And that's already been used effectively to support specialized compilers for these accelerators, both on, I guess, we've seen we've seen great success with this on traditional operating system targets, and I think we're looking forward to reusing that on microcontrollers as well. So, excellent.
Thanks a lot, Andrew, for that. So thanks, Andrew, once again for that really interesting talk and the demo as well. I'm sure that the community really appreciated that, and we had some great questions as well. Once again, I would like to thank all our sponsors, without whose support, these presentations and talks would not be possible. ARM, the software and hardware foundation for tinyML. DeepLight, they use AI to make other AI faster, smaller, and more power efficient. Edge Impulse, tinyML for developers. Maxim Integrated, the new Max 78,000 implements AI inferences at over 100x lower energy than other embedded options. Now the edge can see and hear like never before. Kixo, AutoML for embedded AI, automated machine learning platform that builds tinyML solutions for the edge using sensor data. Reality AI is for building products. SynSense builds ultra-low power sensing and inference hardware for embedded mobile and edge devices. With that, let me remind you that there is an upcoming talk in the next tinyML meetup. This is going to be on the 2nd of February, which is the Tuesday. And this time we have Martino Sorbaro, an R&D scientist from SynSense, who's going to be talking to us about always-on visual classification below 1 milliwatt with spiking convolution networks on Dynap CNN. The webcast is going to start in the usual time, 8 a.m. Pacific time. And in case you are interested in presenting in any of these talks, whether at the the usual tinyML sessions or even at the local meetup, in this case the tinyML Tokyo chapter, feel free to reach out to us at talks@tinyml.org. And once again, I would like to remind you that the slides and the video of today's presentation is going to be available either tomorrow or in the next couple of days, both at the forum as well as on our YouTube channel. In case there are any pending questions for Andrew, feel free to post that in the tinyML forum, and we can relay that back to Andrew and take it further. So thanks, Andrew, once again for your time today. In case there are any questions from the community, I'll pass them on to you later on.
Great, thanks so much for having me, and it was great to present. Thanks so much.
Thank you, everyone, and have a good day. And see you again in the next tinyML talks.